Okay, so I'm actually recording this twice. So welcome. Under these weird circumstances, I wanted to meet with you folks. Hold on a second. I wanted to meet with you folks because I wanted to do a couple more examples on chapter 4 on circular motion, and then I want to talk about the lab. And I think, probably to be fair, we'll have the exam on Thursday. You guys okay with that?
Yes. 100% okay.
Okay. So we'll have the exam on Thursday. So Tuesday in recitation we'll use it to prep. You guys can see the PowerPoint, okay?
Mm-hmm.
Okay. So we'll have another quiz and recitation on Thursday, and then we'll do some prep work for the exam, and then I added a day to your homework, so it doesn't show on it doesn't show yet on Canvas, but it does show on WebAssign. Always check WebAssign for the due date. Okay, always check WebAssign for the due date on the homework. Because I don't always update it on Canvas. I just forget sometimes to update it on Canvas. Okay. I'm hoping Canvas is open tomorrow, so when I talk about the lab, you can come in and do the lab tomorrow. Okay. All right. I am going to skip the material on relative motion. So you are now responsible for the material on relative motion. But I've done relative motion problem already. You know that, right? The elevator problem is one of them. But I'm going to skip it. I usually don't spend much time on it anyway, because we will be behind, but I'm sure we'll catch up. Okay. So quiz 3, Tuesday, exam on Thursday the 15th, and make sure you pick up your graded papers in D118. Now the labs. If you could turn it in tomorrow, that'd be great. If not, if the campus is closed tomorrow, I'll have you guys turn it on Tuesday, okay? Everyone clear on that? And if there's a problem with you coming to campus tomorrow, just email me the lab and then turn in the hard copy on Tuesday. You guys okay with that? Yes, no? You guys there? Okay.
Yes.
Yeah, and by the way, it's better for me if you blurt out stuff, questions or whatever, because sometimes I'm kind of far away from, like if I'm this far away, if I'm right at the board, I'm too far away from the computer to be able to see the chat, and I might miss some questions. Okay, I'll try to check the chat box, but if you type something in and I don't respond to it, just blurt it out. Don't worry about it.
So is the lab due tomorrow or?
Well,
today?
yeah. I would like for you to turn it in tomorrow, but if you can't come to campus tomorrow, at least to show proof that you've done the lab, email me the completed lab, and then turn in the hard copy next time you see me.
All right, thank you, Professor.
All right, does that make sense? Because I've done it with some folks, because I know it might be inconvenient to come on Friday.
If we go on Friday, do we just bring it to your office and?
Yeah. And
do
then you can just slide it in my office door. I'll be on campus tomorrow.
Okay, cool. Thanks. Is lab open tomorrow if the campus is open?
If the campus is open, lab will be open.
Okay.
Yeah. I'm worried because of that fire, because I'm worried I'm guessing the air quality in the morning will be bad, and then it gets better at like 10 o'clock, so we'll see. But yeah, slide the lab under my door. I'll be around, so you can, if you see me, just give it to me. And I will have a place in the lab for you to turn in stuff too. We'll talk about that next week. Okay. All right, so let me get started. I want to do some circular motion examples. Last time we talked about circular motion, And for uniform circular motion, we derive an expression for the centripetal acceleration. An object's going in a circle at constant speed, it's accelerating. The acceleration is given by the tangential velocity squared over the radius of the circle, and its direction is directed towards the center of the circle. This r hat is a unit vector that points, don't forget the minus sign, away from the center of the circle. So if I draw a picture of an object moving in a circle, I think somebody might need to mute themselves. So let's say an object is going around the circle counterclockwise. Okay. The vector r is the radius of the circle times cosine of theta times I hat, and then the other component this term in parentheses is a unit vector, and this unit vector is directed away from the center of the circle. This is called the unit vector r hat. So this is this thing in parentheses. Another way to, instead of writing all this, you can write that. But it's always pointed away from the center of the circle, and then the acceleration vector is pointed towards the center of the circle. I derived A the other day, and I did make a mistake on the board. Okay, A looks like this. Okay, where the minus sign is the minus r hat term. I had the sine and the cosine switched, and I always keep doing this. We also said that for an object moving in a circle at constant speed, omega times t is theta. The period is related to omega by this following equation. And the frequency is 1 over the period. These are the main things we talked about the other day. So what I want to do is an example. Any questions on this? Okay. So we also talked about the theta hat direction. We also said that the velocity vector, if you take the time derivative of this, if you put omega times time here, if you take the time derivative of this, you get v is r omega sine omega t I hat plus cosine omega t j hat. This thing over here is a unit vector. We call it the theta hat direction. It's tangent to the circle. Okay, the theta hat direction is tangent to the circle. And positive theta hat is counterclockwise. This is just FYI. I'm not going to have you work on polar vectors. Okay, just so you know, because you'll see it later on in other courses. Okay. All right. So let's do an example. Have a merry-go-round. If I want to do this for you. You have a merry-go-round, 2 meters in diameter, rotates at 10 revolutions per minute. What is the acceleration of a child who's riding on the perimeter? Okay, so let me draw a picture. I'm going to draw the top view of this because it's easier to interpret from the top view instead of from the side view. And here's my merry-go-round. And here's a person right here, a distance r away. This is 2 meters. And we want so this person's going in a circle. We just want the magnitude of the acceleration. We want a sub c. We're given 10 revolutions per minute. What kind of quantity is that?
Would that be the period?
Not exactly, because the units are per unit time, right? If it was the period, it would be seconds or minutes. This is per minute per second, so it's 1 over the period. This is a frequency.
Doesn't it say that the diameter is 2 meters?
Oh, the diameter is 2 meters, sorry. Thank you. There's 10 revolutions per minute. How many revolutions per second is that? In other words, it makes 10 full circles per minute. How many revolutions in a second? Well, there's what? 60 seconds in a minute?
Would it make 1/6 of a revolution
Yeah.
per second?
Okay, so the frequency is 1/6 of a hertz. So what's the period then?
6.
6 seconds. Because if it makes a revolution in 1/6 of a second, I'm sorry, let me rephrase that. If it makes 1/6 of a revolution in a second, then it takes 6 seconds to make a full revolution. And we want to find a sub c. A sub c is v tangential squared over r. Well, what's v tangential? It's the average speed, or the instantaneous because the speed's constant. Circumference, or the period, is 1 over r. And when you do the calculation, you should get 1.1 meters per second squared. Questions on that? Is there another way I can figure this out? Well, yeah, I can write this equation a lot of different ways. Because what do we say is 1 over the period? Right? 1 over the period is the frequency. But what's 2 pi f? Remember, we had this equation before. Okay, so that's another way to write it. In fact, I could have just put 1/6 in here and solved it. We okay with that?
So you said you would have put 1/6 in for W, correct?
No, for frequency. Omega, remember this is omega, not W.
What's that? Sorry, Morgan.
So it'd be 2 pi times the 6. What is 2 pi times the 6? 2 pi times the 6. Pi over 3? I'll make this pi over 3 here, right?
I don't think it's
Okay. All right, let's do the second question. We have a conical pendulum, and I don't have one with me. Has a string that's the length of a meter long. When the pendulum is rotating with a period of 2 seconds, the string makes an angle of 68 degrees with the vertical. What is the acceleration of the pendulum? I kind of got to, we got to draw this picture correct. You all know what a pendulum is, right? You all know a regular pendulum, right?
Yes.
Okay, so conical pendulum is constructed basically as a simple pendulum, right? You have a string and a mass. Regular pendulum, the object goes like this, right? In the conical pendulum, this thing swings in a circle. It actually sweeps, as the object swings, it sweeps out a cone. I don't know if I can do it with this. This thing's going to fall apart on me. So, this is a conical pendulum. Okay? This is a simple pendulum, what you're familiar with. But a conical pendulum sweeps out a cone. So the object at the bottom is sweeping out a circle. And because the object at the bottom is sweeping out a circle, there's a centripetal acceleration. There's an acceleration towards the center of the circle. And so we want to figure that out. Let me draw this a little bit better. This is the vertical. This is 68 degrees. That's the circle that sweeps out. This is the radius of the circle. So sweeping out this circle as it swings around. Okay? And we're given that the length of the string is 1 meter. What's the radius going to be then? What's the radius of the circle sweeping out from your trigonometry? Opposite or hypotenuse. Okay. What else are we given? The period is 2 seconds. So A sub C so let me simplify this before I plug numbers in. Last time I just plugged numbers in. Let me simplify this. This is 4 pi squared r over t squared, right? Does it look okay? This comes out to about 9.15 meters per second squared. Have you all seen that amusement park ride as you're going on 80 west? You're going towards Sacramento. Have you all seen that amusement park ride that swings around?
the Scandia Screamer?
Yeah, the Scandia Screamer, right? Have you seen that? So, just want to mention something about that ride. Every point on this device, on this thing, as it swings around, is making a circle within the same time period. Right? Every point on this thing spins around, the Scandia screamer spins around, every point on this piece sweeps out a circle in the same time period. But what happens to your tangential velocity as you get further and further away from the center of the circle?
Does it increase?
It increases because, remember we said V tangential is omega times R. Remember that if the basket in that ride's here, this circumference is small, right? If you're over here, this circumference is huge. In both cases, you're completing the full circle in the same time period. The difference here is that at the end, you're completing a very huge circle. And I think at the end of that ride, if you're at the end of that ride, you're moving at 60 miles an hour. That's because V is omega times R. Okay?
So would that mean that in that case, the acceleration will be different, but velocity is the same? Or
The angular velocity is the same.
okay.
The velocity is different. And the centripetal acceleration is different as long as V is different. Right? Since A sub C has a V in it, if V changes, A changes in magnitude.
Got it. Okay.
Okay. And so the bigger R is, remember this goes as R squared, V tangential. The bigger R is, then the greater the acceleration, assuming omega is the same value. Remember A sub C is omega squared R. Okay. So you can imagine the acceleration is huge on the end of that ride. What if speed is not constant? You're going in a circle. You're over here. So the radius R. Going like that. But what if omega is not constant? This is your tangential velocity. If omega is not constant, then be tangential not constant. And if that's the case, then there is an acceleration tangent to the circle. And the one towards the center of the circle still exists. So you actually have two parts of the acceleration. You have one that's tangent. You have a tangential acceleration. Sorry, it's not that very dark. And then you have a radial acceleration. So you have two components now if omega is not constant. Okay? So you have a tangential acceleration and you have a centripetal acceleration. So you have two components. So A tangential is dv dt, and A radial or A centripetal is still b tangential squared over r. So this value changes because this changes. It's still directed towards the center of the circle, it's just that the magnitude changes. Right? The direction always changes, right? Because as you go in a circle, even though this points to the center of the circle, the direction relative to us is different, right? Because when you're down here, this vector points that way, as opposed to this way. So you have two components, and when we get to chapter 10, we're going to talk about a little bit more about how to calculate this. What you need to know how to do is find the resultant vector. Can you find the resultant vector of these two? Well, yeah, you just use the head to tail method, right? So I'm going to take from A sub r, and my resultant vector is this. And I always measure my angle with respect to the radius of the circle. Okay, I always measure my angle, or I should say, it is standard to measure that angle with respect to the radius of the circle. Can I also write it in terms of x and y components? Sure. Is it going to take a little bit of work? Sure. One of your homework problems has you do that. And one of your homework problems has you play with this. Okay? So let's do this example. At a particular instant in time, and we can only focus on an instant in time because we have a tangential acceleration here. An object is traveling in a circular path of radius 2.5 meters. It has an acceleration of 15 meters per second squared at an angle of 30 degrees with respect to a line drawn radially to the object. At this instant in time, what is the speed of the particle and its tangential acceleration? Okay, so I need to draw a picture. Let me erase this. I'm going to draw a similar picture, but let me erase this. Okay. Object going in a circle. We're doing everything relative to the radius, so it doesn't matter how I draw this. Okay? So, let's say I draw the object right here. This is the center of the circle. A sub c, or A radial, is that. It says that it has an acceleration of 15 meters per second and an angle of 30 degrees with respect to a line drawn to the radius. So I'm going to draw a hypotenuse of the triangle. Let me draw a piece of T first of all. And then this is the hypotenuse formed by the two accelerations. Oops, that's not good. The arrow point is points to the other way. We're given that this is 15 meters per second squared. I want to figure out A tangential. How do I get A tangential? Don't I have a right triangle there? Well, the answer is yes, I have a right triangle there. Okay? And this is opposite the angle, so isn't it true that A tangential is 15 meters per second squared, sine of 30 degrees. What's the sine of 30? Anybody know? You should know.
1/2.
Yeah, so a half times 15 is 7.5. So how do we find a centripetal? How do I find B tangential? I saw this for B tangential. And I'm running out of space. What was the radius? 2.5? Okay, and I don't have the answer written down, so let me calculate it. 5.70. So that's the centripetal acceleration. Okay. The way I drew it, I made the problem convenient because I made A sub c horizontal and the other one vertical. But if this thing was rotated by like 40 degrees, then the math would be a little more complicated because you have to do a little bit more geometry. Suppose you guys got to answer this question. Omega was this way. What does that mean? If A tangential points in this direction. Is speeding up or slowing down?
Are you saying if the object is rotating in like the counterclockwise direction and the acceleration is going clockwise?
Yes.
It would be slowing down.
That's right. Right, because at this point, V tangential is upward, but A tangential is downward. Remember, if V and A are opposite to each other, the object is slowing down. And be aware you can be asked these questions. You'll see this question on the homework or on the exam. Okay, so I expect you to understand this. I expect you to understand this drawing. There's a great homework problem where they do this at an angle, and you have to figure out everything. So the only thing hard about it is geometry. This is a geometry problem. It's the same problem, except you're doing geometry. Okay? And guess the best way to solve that problem? What do you have to do to solve the problem? Right, if I had this whole thing rotated, what's the best way? You draw a picture. You make sure you draw a good picture. You draw a big picture. Don't draw a picture, like this. Okay, draw a big one. And then you can solve it. If you draw a good picture, you'll be able to solve that problem. If you don't draw a good picture, it'll be hard. Okay? The more care, in these particular problems, the more care you have in drawing a picture, it really goes a long way in helping you solve the problem. Okay? All right. One last thing I want to say about circular motion. All right, I'll be honest, this is really in chapter 10, but I can cover it now. Let's talk about the rate at which the angle changes. I mean, look at these equations. The definition for EV average and the definition for omega average, they're the same mathematically, aren't they? You can give thumbs up if you want. Okay, look at it. Same, the definition for V and the definition for the rate in which the angle changes is the same. The definition for A is the same as the definition for the rate in which omega changes. We call that the angular acceleration. Okay? So alpha is the rate at which the angle changes. Okay. So remember, d theta dt equals omega. The omega over dt is called alpha. Alpha is called the angular acceleration. In fact, if v tangential is r omega, guess what dv tangential over dt is? Well, if an object is going in a circle, this is constant. We call that the tangential acceleration. So, let's say the tangential acceleration, well, let's go back to chapter 2. Let's go back to chapter 2. In chapter 2, we said for constant acceleration, for constant linear acceleration, that's how x is, for constant a. What should theta look like for constant a? Do I have to do something complicated, or can I just write the answer down? I can just write the answer down. What's the analog of x naught if I'm talking about angles? Theta naught. What's the analog of initial velocity? The initial angular velocity. What's the analog of acceleration? The angular acceleration. So we can write theta as a function of time right away without me having to derive all that. I'm just doing analogies and you can get it. And you'll see that if you look in chapter 10, you talk about this. So, very quickly, so we understand these definitions. You're given theta as a function of time like that. Let's find the angular acceleration. Let's find the average angular acceleration between 1 and 2 seconds. And let's find the average angular speed between 1 and 2 seconds. Okay, so we're given theta as a function of time. Theta is 2t minus 5t squared plus 2t to the fourth. Omega is d theta over dt is 2 minus 10t plus 8t cubed. So what's alpha? The angular acceleration. Check my math. Okay, so I want to calculate the angular acceleration.
Is that negative 10 or positive 10? T.
Oh, negative
10.
10, thank you. So we want alpha at t equals 1 second. So alpha at t equals 1 second is minus 10 plus 24 times 1 squared. Okay. And I haven't been careful with the units, I apologize. What does this come out to be? I think I mentioned the other day that omega is in radians per second and alpha, omega is in radians per second. Radian is not a physical unit because it involves an arc length over radius, and so you can still write it like this in physics class.
Why is it negative?
because I screwed up. Thank you.
Oh. Okay, thank you.
Yeah, I don't have the answer, so I'm doing it off the top of my head. Now, how do you find the average angular acceleration? You got to be careful. Alpha average, by definition, is omega at t equals 2 minus omega at t equals 1, divided by my time interval, which is 1 second. Okay. If we plug in 2, help me with the math. If we plug in 2 seconds, 2 minus 20 is negative 18. And then, this is 8 times 8, right? 64. 64 plus 18 is 82. Did I do that right?
Was it 64 minus 18?
64 minus 18. So 64 minus 18 was at 46. And then let's do it at t equals 1. So help me out. 2 minus 10 is negative 8. Right? Negative 8 plus 8 is
0.
And how do I get the average angular speed? By definition, how do I write down here? Okay, let's plug in k equals, I got the numbers in now. 2 times 2 minus 5 times 4 plus 2 times 16. Okay, 32 minus 20 is 12 plus 4 is 16. Did I do it right? And in the other case, I plug in 1. 2 plus 2 is 4 minus 1. I'm sorry, minus 5 is negative 1.
What's the formula you're using for this one to calculate the theta, because we can't really see the top part of your board?
Oh, I'm sorry. Let me fix that.
Okay, got it. Thank you.
We okay with that? Okay. So, I actually want to check the time. I'm using a good computer. Okay, got 2:40. So the rest of the time, I want to talk about the lab. So I arrived at campus and then I found out the classes were canceled. So I took some pictures of the apparatus. And so I'm using pictures and taking filming because filming is always harder for me. So before I talk about the experiment, I have a few comments. And I don't know if you might have seen the email, and I have a lot on the slide. I probably shouldn't have that much on the slide. So regarding the sig fig worksheet, if you lost a lot of points, it's basically because you forgot to calculate the percent uncertainty in each propagation exercise. Okay? That's why you lost, if you lost like 7 points, you probably forgot that. Because each one, the propagation exercise was worth 14 points. Okay. If you weren't happy with your lab grade, don't worry, it'll get better. I'm pretty sure if you work at it, your lab report will get better. Okay. If you understand the mistakes you made, then your lab report scores will get better. That's the trend in this course. because you're trying to get up to speed as to what's expected. Because at the beginning, it's hard to either understand or either believe the instructor is going to expect you to do certain things. And so, some students don't do it and they get a little score. Okay? But then later on, students understand what's expected in the lab, what the meaning is of all these things we're doing. And you get better, and lab report scores get much better. Okay? So don't worry about it if your lab score was lower than you expected. It'll get better. Please pick up your graded lab reports from the basket on the wall in V118. Like I said, I'm also going to put a basket for turning in things, but it'll be in V120. Make sure you staple your lab reports. I do get things that are not stapled. It's really a pain to have everything, the lab stuff not stapled. Please staple it. Okay. And then beginning with the lab I'm going to talk about today, every lab requires a cover sheet. Okay. And I'll write your score of the lab on the cover sheet. The one big thing that everybody needs to understand is that the theory of errors supersedes the rules for sig figs. And that's a hard one to digest because the first thing you all learn is the rules for sig figs. And it's really not what's used in the real world. So I have two examples in this slide. I put numbers in it and I calculated the uncertainty using Excel. And that was fast for me. So I have two examples. And if you notice the first example, if you add up all the numbers, the rules for sig figs say that your average should have 4 sig figs. But because of the large spread of those numbers, the uncertainty is 0.1. And since the uncertainty is 0.1, you shouldn't be quoting your final answer to more than 1 decimal place. Notice how I quote the average value. That's how you should quote an average value. You quote the average and the uncertainty with the units. Uncertainties have units because they represent the uncertainty of what you're measuring. The second example, I made the numbers close to each other. And in that particular case, the rules for sig figs are in agreement with the theory of errors. The uncertainty is 0.005, and if you don't believe me that it's not 0.005, go ahead and calculate it. There's a way to do it in Excel. And that average, I kept at 3 decimal places because my uncertainty was to the 3rd decimal place. Is everyone clear on that? I can provide this PowerPoint for you too. I also want to talk about the different types of errors in an experiment. And physicists love talking about this, and the last one that's on there, I'm going to go on the board. The last one that's on there is the one that drives physicists crazy. So there's personal errors. There are random errors. And there are systematic errors. Personal errors mean you screwed up. Okay? You made an error in your calculation, you followed the procedure incorrectly. These are all correctable. So in the lab, I expect your labs not to have personal errors. If you get 100% error in your lab, I want you to figure out why you're getting 100% error. Don't just change the numbers or anything. It could be you have an error in your calculation. Okay, I had a group once, the first time I taught this course, I had a group who spent like 3 hours doing, it's called moment of inertia lab. And they never showed me what they did, and they just kept telling me that we've been working for 3 hours. The theory and the experiment are way off, 100% error. Then I said, finally, I told them, look, you've been working for 3 hours. Show me what you've done. The data look great. Okay. Then I looked at a calculation theory, the calculation from the theory. And the calculation requires a radius. You can't measure radius directly, you measure diameter. So they took the diameter and put it in the equation when they should have used the radius. And that gave 100% error. Once they put in the right value in the theoretical equation, they got like 1 or 2% error. Okay, they spent 3 hours trying to figure out what was wrong. So if you get a large error, find out why. If it is due to the apparatus, I need to know, because then everybody's results are going to be really bad. Okay? So if you have a huge error, you got to talk to me, you got to talk to Tyler, a tutor, anybody. Figure out what's wrong. Okay? Because it might not be your error, but it could be, an apparatus error. Our job is to make sure the equipment works properly. So we need to make sure so that you can get the good data.
For this lab,
I'm sorry.
I have a question, Professor.
Yeah.
For this lab, we shouldn't have any major personal errors, right? Because we're not comparing a theory to an experimental.
No, you're not. If you measure the diameter, you're talking about the one you just turned in?
The measurement lab with errors.
Yeah, if for example, well, we got to be careful. If you measure the length of the block as 1 meter, then yeah, then that's a personal error, right?
Okay, noted. Thank you.
You know what I mean? If you do something wrong. Or what a lot of people did, I've noticed, when they use the ruler, they had the numbers like this with the ruler. What's wrong with this? If you're using the ruler.
You're supposed to guess to the next decimal point.
Yeah, because that guess is important. Because if the number is between 2.5 and 2.6, I need to know. You are shortchanging yourself by not including the guess. You're making your results look worse than they actually are. You don't want to do that. Don't shortchange yourself. Okay? Same thing with the micrometer. The micrometer measures the 0.001 millimeters. So when you convert that to centimeters, there should be 4 decimal places. Okay. Those kind of errors are personal errors. So that's really the only error, regarding to your question. The personal errors in that experiment are you're not reporting the right number of decimal places, or you got a bizarre number for the measurement. Okay. Or your volume calculations, maybe it's a typo, right? Instead of a number like 15, you put 75. 2.5 times 2.5 times 2.5 is 75. Some typo error. That's a personal error. So you gotta proofread your lab report. Okay. Random errors are what we're talking about. Right? They're errors due to the fact that all tools are imprecise. You can't get rid of it. And sometimes the error makes your value larger, sometimes it makes your value smaller. It's completely random because of the fact that you have a lack of precision of your instrument. Okay? And when I say this in the slide, I said in general, because we can talk about other things. What about systematic errors? There are consistent errors that make your results consistently larger than what they should be, or consistently smaller than what they should be. Of course, it depends on the kind of error we're talking about. So one example is you use a ruler. What if the spacing between the lines on the ruler is less than 0.1 centimeters? What if the lines are consistent less than 0.1 centimeter? That's going to make all your measurements bigger than what they should be, right? What if your scale, so that means this is not calibrated. What if your scale is not calibrated? That's going to produce a systematic error because your results are always, when you weigh something, the object is going to be always too big or always too small, the object's mass. If you have air resistance, if you're measuring the acceleration of an object and you have air resistance, right, and you ignore it in the theory, then you're going to have a discrepancy between theory and experiment, a consistent discrepancy. Air resistance is the most common systematic error we'll deal with in this course. The last one is human error. To a physicist, it's like a 4-letter word. Never use the term human error when you're talking about your experiments. I will automatically tick off 2 points on your lab if you say human error. Okay? What does human error mean? Could mean you screwed up. Well, you might be thinking, oh, I'm using the ruler to guess the last digit, so there's an error as a result of the fact that I'm guessing. Yeah, but that's a random error. Okay, that's just a random. If you're forced to guess the last digit and you do it right, that's a random error. It's not a human error. A human error, I mean, literally would mean screwed up. Never say human error.
I have a question again.
Yeah.
What category of error would for the micrometer when we had to estimate past 25 due to the fact there were no more values on the micrometer?
That's a good question. As long as you're counting the number of turns that you go by every time, then you still have a random error. If you're well, it's generally going to be random error. Unless we know something about what happens after you go past 25 on there. You know, if the manual says if you go past 25, the number of millimeters changes or something. The calibration changes. If they say that, then it is systematic. But that one's hard to know. But my first, without looking at the manual, my first guess would say it's random. Does that make sense?
Yes, Professor. Thank you.
Okay. But yeah, so anyway, regarding one of my pet peeves, if you look at my announcement, don't use the term human error, okay? And you might, and I've heard some instructors in high schools say, what are the human errors in your experiment? That's bad. Okay. So this next lab is your first real lab. You're going to measure something. You're going to measure motion. So you need to sign up for your lab time. So for you guys, there's a sheet of paper in the lab on one of the back walls. I always get mixed up between 108 and 118. But there's a sheet of paper with a grid on it. It says 205, Tuesday and Thursday. And there's a grid on it. I'm not going to draw a grid. Everything is grid. Anyway, it goes all the way to 4 o'clock. And what you and your lab partners want to do is find a time in which you're going to do the experiment. So let's say you want to do Friday. I ran Friday 1 to 2 on my sheet here. I'll just look for the guy. And you put your names in here. And pen. Don't use pencil. Pencil gets erased. Okay, so put your name in there. And you're making a commitment every Friday, or whatever you choose. You're going to come do that in the experiment that time. Okay? So find the time in which you want to do the experiment. The equipment is reserved for you at that time. Nobody else will be working on that apparatus at that time. Okay? And if
I have
there's
a
an
question.
issue, let me know. Yeah,
Can you write your names more than once a week?
I'm sorry?
Can you write your names more than once a week?
No, because it'll be confusing. What will happen, because there's 32 of us and there's like 35 slots, actually, there's going to be at most 16 groups and 35 slots. There's going to be slots where there's an opening, and if there's a time when there's no name in there, it's first come, first serve.
All right.
Okay? If we do groups of threes, then we'll only have like tops 11 groups, so 11 out of 35, it's quite a bit. Okay? So this is a semester-long commitment. So I will say that my lab hours generally, most of them are on Friday, so if you sign up on Friday, I will be here. Okay? All right, the best day to catch me for open lab is Friday, so that's a good day. You might not like Friday, but I'm just telling you. Some of you guys can only come Tuesday or Thursday, so go ahead and do Tuesday or Thursday. Okay. Someone's here, someone's in the lab to help you. Okay. And you already seen that. It was great last Friday. A bunch of you guys came on Friday. It was great to see y'all working at once and asking questions. Okay. So no more than 3 people per lab group. If you need to change your time, come and talk to me. So what if you can't find a lab partner? Well, put your name in this time slot. I already screwed that up. It's okay. I should have put a times here. Anyway, let's say you put your name in a time slot. There might be another person who's on the same boat as you, who needs a lab partner. They see your name there, and they put their name there. It'll be like a blind date, but you'll have a lab partner. And one of the things I want you to do is learn how to work in teams. Okay. So one of the things that's important about this course is the lab is to learn how to work in teams. So I really would like for you to try to work in teams. There are some people who might want to work by themselves. There are some labs you can do by yourself, but a lot of labs require more than 2 hands. That's why I recommend either 1 lab partner or 2 lab partners, but no more than 2 lab partners. Are we clear on that?
Yeah.
Okay. So let me go on to the next item. What is the purpose for this lab? I actually added a lot more stuff than what's in the lab itself. I'm assuming you have the lab in front of you, or I'm hoping you have the lab in front of you. I can switch windows and show you the lab, that's a pain. We want to learn how to measure the motion of an object and to graphically describe the motion of an accelerated object in 1 dimension. We want to measure g. We want to learn more about error analysis. We want to learn more about the difference between random, systematic, and personal errors. We want to learn the difference between precision and accuracy. We want to understand, what does it mean when 2 values agree with each other? Because there's a objective way to figure that out. If normally when you ask somebody the 2 values agree, they'll say, oh, that's close. If you say 2 values are close, you know what I'm going to say? I'm going to say define close. Okay, I define close. And so I want to talk about, and then I might do this at the end to see how much time I have. Okay, how do we assess agreement between 2 measured quantities?
It has to do with the error, right? That the values are within the same degree of error.
Yeah, you look at the range, right? Because you're not measuring g, right? In this slide, you're not measuring. You're not measuring a number, I should say. You're measuring g, but you're not coming up with a number. You're coming up with a range of values. All right, you're going to say my value is 9.80 plus or minus 0.3 or 0.03. That gives you the range of values that your experiments can produce based on the precision of your apparatus. If the range of values produced by your experiment overlaps with the accepted value, then they agree. If not, then they don't agree. So, what are we going to do in this lab? So let me say something about what we're going to do. We're going to drop an object and we're going to measure its acceleration. So what we're going to drop is a weight. Okay. This will be a 50-gram weight, but it's also attached to a tape. And the tape is going to be used to create a motion diagram of the motion of the object. Let me give you an analogy of this. Suppose I told you and your lab partner to go in your car. One person drives, and the other person takes a paintbrush and makes a dot on the road every second. So every time you draw a dot, that means 1 second has elapsed. And the pattern you will have on the road, don't try this though, you'll get in trouble. The pattern you'll have on the road is called a motion diagram. If they're equally spaced, what does that mean?
Constant.
Constant, yeah, you're going at a constant speed. And what if the dots start spreading out?
Faster if they get bigger.
You're accelerating. The dots get spread out, you're going faster. And the dots get closer together, you're going slower. It was like one of the quicker questions I asked in recitation. And so what we're going to do is do something very similar to that, but we're going to create dots on that white tape. You see that white tape in that first picture that's attached to that mass? We're going to find a way to create to actually make dots on that. Well, we have a device called a tape timer. It's that black object that you see. There's a little plunger that goes in and out at a periodic rate. It'll actually go in and out at about 40 times a second. You're going to want to set it to 40 times a second. And you want to set it up so that the paper goes underneath that carbon, the white paper goes underneath the carbon paper so that when the plunger goes up and down, the carbon paper will leave an imprint on the white's tape. So you'll attach a 50-gram mass to one of the paper tape. The paper tape should be, I don't know, about 1.5 meters long. That might be a little bit long, but no more than 1.5 meters long, okay? You don't want to use a lot of paper. The object is probably going to be the weight's going to be about this high off the ground. 1.5 meters, maybe a little bit more than 1.5 meters above the ground. And you're going to run the tape through, like you see in the picture. And the last picture you see, my hand, you can't see my hand, but my hand is holding the paper tape. It's suspending the mass. And I'm trying, when I'm holding that up, my hand is like this, as high as possible. I'm trying to keep the paper as straight as possible because I don't want the tape to slide on that black surface. Why is that?
It'll mark up the paper.
Well, it's not that. I'm sorry?
Friction.
Yeah, friction. It adds friction. Not only that, if you have weight going over the side, that's going to add, that's going to reduce your acceleration. So you actually want the paper to be as high as possible. If you're tall, it's an advantage if you're taller than this lab. We unfortunately have stools to stand on to actually hold the tape all the way up. But you kind of want to hold it up so that it's not on the black thing, the tape timer. I'm sorry, go ahead.
So ideally we want someone holding the slack of the paper so it stays straight.
Yes. But when you let it go, you gotta, you can't let it slide through your hands. You just gotta let it go. Right? Because if you let it slide through your hands, then your hands are adding friction. So guess what a systematic error is going to be in this experiment? Sometimes there's going to be friction in it, whether it's air resistance or something sliding. We can't get away from it. But we get decent results. You'd be surprised. So, you set this up. You see the switch on there? And you see it in the bigger picture. You see there's a switch that says Hertz 40 off and 10. You set the switch to 40, and then you'll hear the plunger going in and out, and then you release the mass. Okay, I did that this morning when I found out our class was canceled. And this shows the object really at two different locations after I've let it go. Okay, and that piece of tape that I had was way too long, unfortunately. I think it's like 2 meters long. It should be like 1.5 meters. And then your data you have your data. So it takes us like a second to run this. So that piece of tape is so important. Okay? Hold on to that tape until you know your data is good. Don't throw away that tape until you know the data is good. So now you got to collect the data. You have a piece of paper. Hold on a second. You have a piece of paper with a bunch of dots on it. And what you'll see is the first set of dots are like right on top of each other. And you know it's accelerating, right? So you'll have a bunch of these dots. These are completely useless. Why?
They're too close to be able to measure the difference.
Yeah, you can't measure the difference. You want to be able to resolve one dot from the other. So I'm going to start measuring here. This is my origin. Okay, and then I'm going to start measuring this distance. Then this distance. I'm always measuring the total distance traveled. I'm measuring the position relative to this dot. Okay, so we'll call this x1, x2, x3, x4. Anyway, you'll have like, I don't know how many dots, but quite a few dots. And so you got to measure this distance, etc. And so it actually helps to have a lab partner because you have someone checking your results because, like, for someone like me, my eyes are going to get tired looking at their ruler. Okay? My eyes are going to hurt looking at that ruler. So having a second person checking to make sure you measure correctly is important. So checking, help each other out. Check to make sure that everything looks okay. I've actually had some groups, what they've done is each person in the group measure these, and then in the lab they report the average of the three measurements, and they give me a long paragraph about what they did. It's up to you. If you do something different in the procedure, write down what you did differently. Okay. If you want to add, if you want to do something fancy like that, you can. And so you're going to collect all this data and enter it into a table. But I want to say something about collecting the data, how we gather the data. I don't know if you can see very well. I put a sample of the dots, how faint. It just shows you how faint the dots are. They're kind of faint. Okay, the one I did this morning, this is the one Tyler did, but the one I did this morning is much fainter. I actually had to draw X's on the dots so I could see them. Okay, so the carbon paper helps make those dots. If they're too faint, you see the picture on the right. That carbon paper, if you rotate that disc, you might find a piece of carbon, a piece of the paper that's unused. And then you can run the experiment again. And then maybe your dots will show up better. If the dots keep not, if you still have trouble with the dots showing up, just let us know. We'll replace that piece of carbon paper. Okay, but it should work okay. Everyone clear on that?
Yeah.
So then you take that paper and you lay it on the table in the lab. You tape it down with scotch, not scotch tape, but we have masking tape. And you put a ruler right next to it, a 2 meter stick, because it's going to cover more than a meter, so we need a 2 meter stick. They're brand new, so you can actually very clearly see the numbers on it, as you can see from the picture. Okay. So I've laid the object on the table, and notice the orientation of the meter stick. In fact, you can see it clearly here. I have it on its side, right? You know why I did that? See the X's? Can you see the X's on the slide? I actually wrote in pencil on the X's because the dots were faint. You can do that. You notice how much easier it is to determine the value of the reading when you put the meter stick like this? Most students, guess what they would do? They would lay it flat. If you lay it flat, it's much more difficult to make the measurement. So this is good practice. Okay, notice how I put the meters up, not like how most people, they lay flat. Okay, and they take their measurements that way. Does anybody have any questions about this? Okay. Then I fill out a data table. I made up these numbers. So let me say something about the data table. Okay. There's 2 data tables. So I made up some numbers. They have nothing to do with what you're going to get. Except, in fact, my data there is perfect. Just because I can, this is for example purposes. So the time is electronic, makes 40 dots a second. That means every dot represents 0.025 seconds have elapsed. And so I'm not going to put the t equals 0 point here, because t equals 0, x is 0, so I don't care. And so I have some data I made up. Okay, these numbers, we're going to pretend they're exact because it's the measurement's electronic. So they're not going to play a role in the sig figs. One of the things you will do is you're going to get practice with sig figs. So in this data table, you're going to get practice doing with sig figs. So you're going to get this data, and you're going to plot position versus time. We'll talk about the graph next week. So the first 2 columns are going to allow you to plot position versus time. Okay? Then we need to calculate delta x. Delta x is this minus this, right? This is the distance between dots. Oops. I had a mistake in the 9, I have a mistake in my sig figs. I don't know if you guys noticed it. That's what happens when you're in a hurry. If you look at the slide, this has a 0 missing in the slide. Bad feedback. Okay, so now I'm going to calculate the average velocity. Average velocity is delta x over delta t. Delta t is always 0.025, it's exact. You can have as many sig figs as you want. So what's 3 divided by 0.025? Well, let me rephrase that. What's 3 divided by a 40th? What's 3 divided by a 40th? It's the same thing as 3 times 40. Did you see what I just did? I put the times 10 to the second here. You know why I did that? Because I'm going to have zeros here, and they're going to be ambiguous. Look in the slide, I did that too. Look at the red box. I added that. 5 times 40. 7 times 40. So this gives me the average as a function of time. Does that do any good for me? Probably not, because the velocity is constantly changing. But if I say my time interval is small enough, then I can approximately say it's the instantaneous velocity. But we can do better than that. We know calculus. We know a lot about math and graphing. Don't we? If the velocity is constant, and I talked about this in class. If the velocity, if the acceleration is constant, the graph lies on the slope. Where's the average between these 2 points? Isn't it halfway between? In fact, this average number represents the velocity right here. This average number represents the average velocity between 0.025 and 0.05 seconds. This average velocity represents the instantaneous velocity halfway between these two, and so forth. So I can really plot instantaneous velocity as a function of time. That's what that second data table is. I shifted the time in the second data table. So now I have instantaneous velocity as a function of time. I can plot instantaneous velocity as a function of time, and the slope of the graph is going to give me g. We'll talk about the graph next week. Okay? So now I have v versus t. First and second column of table 2. I can still calculate a. Again, notice the stuff in red. I added those. You can add those so that you get rid of ambiguity and sig figs. When every time I subtract, in this case, delta v is exactly the same, 0.8. And you've got to be careful with sig figs. Then the last column, I take delta v and divide it by a 40th, which is the same thing as delta v times 40. And so I got my acceleration. Notice the number of sig fig varies. You're going to calculate the average of all those numbers in the last column, and you're going to compare it to the slope of this graph that you're going to make. And you're going to plot x versus t. You're going to extract a from this graph, because you're going to do a curve fit. You're going to compare the a from here, and then the a from averaging the last column in table 2. The question is, which one do you trust the most? Look, you guys are going to come to me. Now show me, this always happens. You're going to come to me and say, does this data look good? Well, how do I know? By looking at the table. What's the best way to know if your data looks good?
Asking if it makes sense.
Asking if it makes, but it's hard with just numbers. Somebody else has said something else.
Would it be to graph it
Yeah,
so you can see?
absolutely. If your data forms a parabola, your data is good. Okay. Graph, get the parabola. See if you get a parabola. Okay. The graph will tell you. You know why the graph is better than the data table? Because the graph organizes your data. The graph allows you to show systematic trends. I have no clue if your data looks good. Okay? Because I can't do the curve fit to your data in my head that fast. I have to, it's hard to do a curve fit in your head. Okay, so I can't do it. But if you graph it, you can tell, it's visual, you can see right away if your data is good. And so if you come and ask me, I'm going to say, did you plot the data? Okay, because and I'm being honest with you, I can't tell. Okay, you're asking me a question that it's really impossible to answer. Because all the numbers are going to be different. Oh, I forgot one thing. What can you say about the initial velocity you will get for this experiment? Will it be
It's not 0 on that graph.
Why? Why is that 0? Why would it be 0? I'll exaggerate. Where are you starting at? You're going to start here, right? If that's your tape, you're going to start over here, you're going to start over here.
To the right.
Yeah, you're going to start here, right? Is it moving at this point?
Yeah.
Yes.
Yeah. So when you graph it, you're not going to get a 0 y. It's going to be small, okay? It'll be a small, and it'll probably have a very big uncertainty in it. Don't worry about that. Small numbers are hard to measure. Right? You don't expect it to be 0 because you're not starting at the first data point. Right? You're not starting at the first dot. So you shouldn't expect it to be 0. Okay. If you run out of space in your table, I mean, if you need more space in your table, I would copy and paste another one. That table is horrendous to make. So I would just copy the table and paste one below it. Okay, those tables were really hard to make. I don't know who made them, but to add rows to it is horrendous. Okay. Any questions?
The amount of lines on the table, is that the exact amount of data we need to collect?
No, it's going to vary. That one's going to vary because it's going to vary depending on how many good data points you have on your tape.
Okay.
I mean, ideally you want to have like, the more the merrier, right? So, because if you have 5 data points, you're going to get terrible results. If you have 15 to 20, then you're probably going to get good results. All right. I think the one I did, I had 15. The one I did this morning, I had something like 15. Because I couldn't see the other ones. Okay. So good ballpark figure is around 15. Okay. But if you have 5, you're bad. I'm going to duck points if there's 5, but ideally you want to have 15 or more. And so it'll be close to that data table is going to be close to being full. I forget how many lines are in that data table. I don't know.
I have a question.
Yeah.
Will these slides for the lab be available on Canvas for us to reference?
Yeah, I'm actually going to. Yeah, I'm going to email them to you. In fact, I'll probably email it to my Monday, Wednesday class too.
Okay.
Since I spent I basically spent the whole morning making these. Yeah. So what I recommend that you do this week: collect the data, fill the data table. That's all. Okay. If you can do that, then you're in a great position for next week. Oh, collect the data, fill the data table. Do not throw away that tape. Because I can tell, if you have bad data, I can tell just from looking at the tape if you make what mistakes you may have made. So don't throw that away until we know that the data is good. Okay? All right, let me just ask one more thing. Let me just say one more thing, because I did this with the other group. We alluded to it a little while ago. Let's say, do an experiment. One person gets the magnitude of A. And another person gets okay. So first of all, does this value agree with the accepted value? These two don't agree. Why? Because the range of values, it goes between 9.42 and 9.58. This is not in that range. If I plot that data point, I get something like this. This data point's over here. So this doesn't overlap with this range. So they don't agree. But this one does agree with it. Right? That data point is like this. Which value do you trust more? I will tell you this. You should trust this one more. Why? Because it's more consistent. You have better precision. Precision means consistency. You're going to get inconsistent results with this. The fact that you might think that you trust this one more is because of the fact that you're jaded by the fact that you know what this number is. But what if you don't know that number? Now, these two values don't agree. Why? What does that tell me if these two values don't agree? What kind of an error am I assessing here? At least what kind of error are we learning to assess in Physics 205? We're learning to assess random errors. So I'm only assessing random errors, and this value is not within this number, right? This 9.80 does not fall within this range. That takes no account of random errors. So what does that indicate? It indicates there's another kind of error called a systematic error. So if the two values don't agree, that probably indicates you have a systematic error, like air resistance. Okay? That's generally what that means, indicative. I didn't say it is, it's just indicative of it. Does that make sense? So if I can figure out a way to get rid of my air resistance, I can get an experimental result that's 9.80 plus or minus 0.08, which obviously is much better than that. This time they got cheap equipment. This time they got good equipment. Essentially. Now, somebody might make an offhand comment. Okay, yeah, this had you're trusting this more, but what if this number was 5,000? But okay, we're trying to use some judgment here. Okay, what I'm saying is not going to work in every case. But if this number is 5,000 and this was 9.8, I'm going to say something's way off here. It's 5,000 plus or minus 0.08. Okay, then it says something is way off. I probably wouldn't trust either one of those values. Okay, and next week we'll talk about precision and accuracy in graphing. Thank you for staying. I'm amazed at how many of you guys came. And then we started at 24, 25. So thank you. So this is what I'm going to do. I will post. I might add a couple things. I spent so much time on that PowerPoint. And then I'll probably email them to you. I don't know, or I'll post and I'll put it on Canvas, I guess. And then the video, I'll give you the Zoom link to the video. And then this video, I'm videotaping it twice on my Mac, and so because I was worried if the power would go off. Once it's saved, I can upload it to YouTube because I have a YouTube channel. Although most of that stuff is Physics 210 stuff. I have a YouTube channel, and I can give you the link to the YouTube video, and then you can watch it. Okay, so hopefully I'll see you tomorrow. If not, have a good weekend. Thanks for showing up.
Excuse me?
Go ahead.
I wasn't here for the weekend, or I wasn't here for like the first couple of minutes because I was doing something.
Yeah.
What do we do for in the lab for the Thursday class, like the turn-in for that?
Oh, the turn-in. So, turn it in. Well, it's supposed to be turned in tomorrow. If you can't come to campus tomorrow, what you can do is email me so that you're giving me proof that you finished it, and then you can come next week and give me the hard copy.
Okay.
I'm hoping that's fair.
Yes.
Okay.
I could probably make it tomorrow. I just got to put it into the schedule of stuff I'm doing.
Okay. Yeah, I'll be around tomorrow.
Okay. Thank you.
Okay. Does this sound okay? I just noticed my good microphone wasn't plugged in all the way.
It was fine.
Good.
Okay, because when I use the computer mic, it sounds like I'm in a tunnel.
This one sounds better. It sounds better
Yeah,
now.
I screwed up. It wasn't plugged in all the way. Sorry. I didn't see that. All right, so you guys have a good weekend.
I got one more question.
Yeah, go ahead.
If campus is closed tomorrow, then I imagine you just want us to email you our labs.
If campus is closed, yeah, and then give me the hard copy.
Okay.
I'll send you an email. If I hope they don't close it, but we'll see. Because the air got cleared pretty quick.
Mm-hmm.
It depends on how the wind blows. Okay, we'll talk to you later.
Thank you, Professor.
Sure, no problem.